XYs are not going to close out damped, but I believe that's okay.
The biggest rocket in history begins not with an engine, and not even with a spaceport. It begins with an ordinary roll of stainless steel, almost the same kind used to make kitchen sinks. And a few weeks later, this roll will become Starship, a rocket that together with its booster is taller than the Statue of Liberty. And all of this happens in one place, Starfactory, Texas. 13 football fields under one roof. And one almost insane goal, to build one spacecraft a day. 365 a year. But the strangest part begins here, because at the largest rocket factory on the planet, one of the most important parts of Starship is not manufactured at all. Without it, this entire enormous structure would not rise even 3 feet. It is brought here by truck across half the country and installed almost at the very end. What is this part? Why is it not manufactured here? And how does a factory that is supposed to produce rockets every day actually work? Now we are going to find out. Welcome to the channel for the richest.
Luxury life.
Steel that loves the cold. In 2019, Elon Musk explained the choice of material for Starship with 2 numbers. 1 kilogram of carbon fiber, from which they initially planned to build the spacecraft, cost about $135. 1 kilogram of stainless steel, $3. The project was redesigned, and they moved toward the ideal recipe gradually. The first prototypes were welded from grade 301 steel, the same kind that goes into kitchen sinks. Then they switched to 304, and today rolls of an alloy that no one else in the world has move around the shop floor. But price is only half the story. SpaceX created its own alloy, and the company still does not reveal its exact composition. The main thing is known. This steel behaves unusually. The colder it is, the stronger it becomes. For a rocket, this is a gift of fate. At launch, the tanks are filled with propellant cooled to almost minus 292 degrees Fahrenheit. And exactly at the moment of launch, under the heaviest load, the metal reaches its peak strength. And on the way back, when entering the atmosphere, the same body withstands heat from which the aluminum of ordinary rockets would have softened long ago. There is also a third requirement. The factory stands right by the sea, and finished spacecraft will live for years in salty air, the same air from which an ordinary car rusts away after a few winters. So, no rust. And with all of that, the alloy has to bend and weld easily, otherwise the factory simply will not be able to handle it. What exactly the metallurgists mixed into this steel is a secret, but what they do with it next is impossible to hide. It can be seen right from the doors of the shop. A seam in one turn, a strip of steel about 5 feet 11 inches wide and about 0.16 inches thick goes into an automatic machine. A blade cuts off the sheet, the edges come together, a flash of welding, and in front of us there is already not a sheet, but a ring almost 30 feet in diameter, almost as wide as a 3-lane road. The rings are placed on top of one another, 3 at a time or 5 at a time. Then a robotic arm travels around the stack and welds the joint with one continuous smooth movement. One turn, one finished seam. Until recently, everything looked different. The first Starships were welded by hand, from top to bottom, and people in masks hung on scaffolding for weeks. The shop smelled of burned metal. The smell remained, but the scaffolding is almost gone. All the large seams were handed over to machines. People work where eyes and feel are needed. Small details, complex assemblies, places where a robot cannot get in. A welder here no longer builds the rocket from beginning to end. He brings it to perfection. However, with straight cylinders, such a trick works easily, but a rocket has parts where there are no straight lines at all. Water against steel. The nose of Starship is not forged and not bent with a press. It is formed with water. The method is called hydroforming. A sheet is placed on a die and liquid is fed from above at a pressure of almost 2,500 atmospheres. That is about 36,700 pounds per square inch, roughly twice the pressure of the ocean at the bottom of the Mariana Trench. Or, if converted another way, about 35,500 pounds on every square inch of the sheet. The steel obediently settles into the shape like foil. A person does not touch the metal at all at that moment. The entire operation is controlled from a console. The domes of the propellant tanks are formed the same way, and the curved nose panels are sent to that same rotating welding machine, and from them they assemble the tip of the cone, the most recognizable part of the spacecraft. Then it is time for the finished pieces to move through the factory, but there is nothing for them to move on. There is no conveyor at Starfactory. The funeral of the assembly line. For more than 100 years, complex machines all over the world have been assembled according to Henry Ford's scheme. In 1913, his factory launched the first assembly line, and the assembly time for one chassis collapsed from 12.5 hours to 93 minutes. Since then, the belt has crawled through every large shop on the planet. Cars, refrigerators, even airplanes. The scheme is so familiar that it seems like a law of nature. SpaceX decided that it is not a law. Here, the unusual biography of the leader played a role. Elon Musk is the only person in the world who simultaneously runs a car factory and a rocket factory, and at Tesla, his engineers came up with a replacement for the assembly line. Publicly, Tesla showed it in 2023. The method was called unboxed, that is, unpacked. The car is mentally cut into large pieces, front, rear, left side, right side, and all the pieces are built at once, in parallel, at different stations, and at the very end they are brought together into one whole. The rocket engineers did not like that name. A rocket is a tube, and unboxed method would have sounded unserious. So Musk describes the work of his factory with the words linear adjacent flow. It sounds engineering-like. It means the same thing. One task remained. The pieces of the rocket weigh as much as a bus, and they still have to be moved between stations. The solution hangs directly above the workers' heads. Roads under the ceiling. The entire shop is covered by a grid of steel beams. The first thought, they hold up the roof. No, the roof could do without them. The beams are roads. Bridge cranes move along them. Each can hook a section of the spacecraft, lift it vertically upward, and carry it through the air across half the shop to the next station. Below, work continues. Across all of Starbase, according to data from 2024, there are more than 3,000 employees, and above their heads, a nearly 30-foot ring of the future rocket silently floats. At the stations, the sections are lowered onto rotating stands. The stand slowly turns the part, the way a potter's wheel turns clay. The welder does not need to walk in circles with a tool and a stepladder. The work itself drives up to his hands. This is what the factory looks like from the inside. Dozens of pieces from different spacecraft move at the same time, rotate, grow covered with details, and all of this under one roof. Starfactory never builds one rocket, it always builds several. How fast this is can be seen best in contrast, because at NASA the same process is arranged completely differently. A rocket made of packages. 4 years. That is how long NASA, the American Space Agency, needed to launch its new Super Heavy rocket twice. The rocket is called SLS. It was made for the Artemis lunar program, and it is built, without exaggeration, by the whole planet. One piece is made in California, another in the state of Utah, a third in Louisiana. Each piece has its own contractor, its own factory, and its own deadlines. Part of the spacecraft for lunar flights is even manufactured in Europe. Then all this stuff is loaded onto barges, onto trailers, and some of it even onto transport aircraft and taken to Florida, to Cape Canaveral. And only there, in the vehicle assembly building, the rocket is finally stacked floor by floor. NASA auditors calculated in 2021, with this scheme, one launch costs more than $4 billion. At Starfactory, this whole route, barges, airplanes, thousands of miles of roads, is replaced by a crane under the ceiling. That is the whole difference between the pace of once every 2 years and the pace of once a day. But NASA and SpaceX share one principle. Every piece of the rocket lives its own life until the very end. So it is time to cut Starship into pieces and see how each one is born. Top, middle, bottom. Of the 2 stages of Starship, only one needs to be mass-produced, and it is not the one you most likely thought of. The lower stage is the Super Heavy booster. At the top, it is arranged simply, one transition ring that connects it with the spacecraft. But at the bottom, 33 engines and a tangle of pipelines that feed them. According to SpaceX's plan, the booster works like a shuttle. It pushes the spacecraft towards space, turns around, returns directly to the launch pad, and already about 5 minutes later is ready for the next launch. 1 or 2 such shuttles are enough for one launch pad, but the spacecraft need an entire fleet. One circles in orbit for hours or days, a second has gone to the moon, a third to Mars, and that is months of travel. A return spacecraft then waits for weeks until a new payload is installed in it. For launches to happen every day, there have to be many spacecraft in operation, and all of them in different phases of flight. That is what is hidden behind the words "a rocket a day." A couple of numbers for scale. The spacecraft itself is about 171 feet, the booster under it about 230 feet, together more than 394 feet. That is taller than Saturn V, the rocket that carried people to the moon. The spacecraft itself at the factory is divided into 3 parts: the top, the nose cone, and the cargo section. The middle, solid propellant tanks. The bottom, the place for the engines. We will begin with the top, with the part that first meets space and first returns into fire. Click. A female assembler presses a black hexagon against the side, aligns 3 holes with 3 pins, and pushes until a click. That's it. The tile has locked into place. There are about 18,000 such clicks on one spacecraft. But first, the pins. As soon as the nose cone panels are welded, a robot comes and with spot welding covers the entire surface with small studs. These are anchors for the heat shield. Next, the cone moves to the thermal station, and there it is dressed in layers. First, a black fabric, a backup shield in case some tile tears off in flight. On top, white foam. It insulates the body and fills the gaps between the tiles. And only then the hexagons themselves, click after click. SpaceX bakes the tiles itself, and this shop at the factory is called the bakery. The technology is close to the production of ordinary tile or glazed plates: mold, kiln, glaze. The automatic line produces more than 1,000 tiles a day, and the plan is 7,000 a day. To understand why such simplicity is needed, remember the space shuttles. They had more than 24,000 tiles on the body, and almost every one was its own shape, with its own personal number. Replacing one turned into a special operation. SpaceX did the opposite. Almost all the tiles are identical. One came off, they took the same one out of a box, clicked it in, and flew on. And the shape was chosen not for beauty. With square tiles, the seams line up into long, straight paths, and superheated plasma during descent can cut a path for itself along such a seam. With hexagons, there are no continuous straight paths. The plasma has nowhere to accelerate, but how many times the black backup layer has already saved a spacecraft during descent, the company does not say. While the cone grows covered with tiles, nearby 2 smaller jobs are going on. Both will hide inside the spacecraft. What they hide in the nose. An assembler climbs into the very tip of the cone, to where the walls come together into a point and where it is possible to work only bent almost double. He fastens the landing tanks there, 2 small round tanks made from the same stamped steel. The fuel in them is an untouchable reserve for one single maneuver, the final braking before touching the ground. Here, the main advantage of assembly in pieces can be seen. Try to drag a tank to the top of an already assembled 164-foot rocket and run all the pipes there. But when the nose lies separately in the shop at a comfortable height, it is an ordinary assembly shift. The second station at that same time assembles the wings, movable control surfaces that the spacecraft waves during descent the way a skydiver moves his arms. Flat steel sheets are welded to cast frame beams. Each wing has 3 hinge assemblies. The edge is rolled with a strip of steel. Then the wing receives the same heat protection as the body. Meanwhile, fastening points are welded onto the outside of the cone, and electric motors are installed inside, the muscles of the future wings. A crane lifts the wing to the side. The crew pulls everything together with bolts. The ringing of impact wrenches in this part of the shop does not stop. And at the neighboring station during those same hours, they assemble a compartment in which they cut a door outward, straight into vacuum. The cargo compartment. In a body that is required to remain airtight, workers cut holes, deliberately and according to the drawings. The compartment is assembled from 3 steel rings. On one side it is covered with tile and on the other cut. First, a long slot. This is the door. Through it, Starlink satellites will go out into space. There are already more than 8,000 of them in orbit, according to data from 2025. That is more than half of all operating satellites of humanity. Lower down, 2 round hatches. These are docking ports. Through them, 2 starships will be able to connect directly in orbit and pump fuel from one to the other, like 2 cars on a highway sharing gasoline. No production rocket had ever been able to do that before. In parallel, they assemble the device that will live inside the compartment, a cassette for the satellites. Several dozen Starlinks stand in it in a vertical stack. The mechanism clicks them outward one at a time and pulls the line upward. The engineers nicknamed this thing Pez, after the toy candy dispenser that gives out 1 candy with each click. The cassette is lowered by crane into the compartment, the slot is closed with a door, the hatches with covers. The last step of the upper section remains. The tip of the cone is lifted onto the cargo compartment and a robot welds the circular seam. 2 pieces become 1. By the way, this is why Starfactory has a stepped roof, low on the side where rolls of steel come in, and high where assembled sections come out. The building grows together with the rocket, and yes, we have already gone through more than half of the factory, assembled an entire section of the spacecraft, and still have not met the part that is not made here. Everything is right. Its turn always comes last, exactly the same way, in pieces and in parallel, the middle and the bottom are born. Each section has 1 big job and 2 or 3 small ones beside it. And then all the roads of the factory converge at one point. The meeting place. Imagine 6 hypermarkets pushed into one building, and now put on top another 13 floors made from the same hypermarkets. You get Gigabay, a tower about 381 feet tall and with a volume of about 45,900,000 cubic feet. Here the pieces finally become a rocket. The idea itself is not new. NASA has had since the 1960s a vehicle assembly building designed for 4 Saturn V lunar rockets at once. Its doors are such that they take 45 minutes to open, and on the flag painted on the wall, each star is almost 6.5 feet across. Thanks to this building, the agency managed to send 4 crewed missions toward the moon in 1 year. In Gigabay, there are even more stations, 24 for spacecraft and boosters mixed together. That means 12 fully assembled rockets can be born here at the same time. And a second identical Gigabay, the company, in 2025 began building in Florida, next door to that same NASA building. A crane lifts the sections and the top, middle, and bottom become one whole. Next, crews cover the spacecraft on different levels. Some pull fuel lines and compressed gas lines. Others run wiring so that the machine has power from nose to tail. A third group adds the last tiles. Then the checks begin, one after another, a list weeks long. From the outside, the spacecraft looks ready, it shines. But below, under the tail skirt, it is empty. The time has come for that very part. The last part. Residents of the Texas town of McGregor recognize this sound with their eyes closed. SpaceX has been firing engines here since 2003, a roar for many miles, window glass shaking. It is exactly here that what Starfactory does not make arrives. Engines, Raptors. They are assembled on the other side of the country, on a line in Hawthorne, California, in the same place where the Falcon 9 rocket was born. Each Raptor produces more than 200 metric tons of thrust, and this is a machine about the size of a passenger car. The fuel, methane, and liquid oxygen. Methane was chosen with the long view. It can be produced directly on Mars from local carbon dioxide and ice, and spacecraft can be fueled for the trip back. The finished engine is carried by truck across half the country to McGregor, put on a test stand, and fired at full power in flight modes. All the childhood illnesses have to come out here, on the ground. Only after the firing test does the engine go to its spacecraft. Here is the answer to the riddle from the beginning. The part that the biggest rocket factory on the planet does not make is its heart. For now, the heart is brought in, although back in 2021, the company announced that it would build an engine factory right next to the test stand in Texas. The engines are installed last, and not all at once. First, the spacecraft is run through a stress test. It is loaded with pressure, as during a real launch, and they see whether the structure holds. Then, part of the engines are installed, 3 of 6 on the spacecraft or 10 of 33 on the booster, and a static fire test is conducted right on the ground. The fuel lines, electrics, and automation are checked, and only after all the checks does the machine return to Gigabay, receive the full set of engines and a new status, ready to fly. Today, Starfactory builds spacecraft faster than SpaceX manages to launch them. Finished machines stand in Gigabay and wait for their turn into the sky, but this will not last long. As soon as the company entrusts Starship with real work, launching third-generation Starlink satellites, the pace will break loose. There is already a benchmark. The Falcon family in 2024 flew into space 134 times, more often than once every 3 days. Starship must fly no less often. And then the plans pile one on top of another. Orbital data centers, lunar missions where for one landing spacecraft, an entire chain of launch and refuel missions is needed. And Mars, where spacecraft will leave not one by one, but in flotillas. All these programs have to work simultaneously, which means the world will need more rockets than it has seen in the entire history of spaceflight. By the way, the settlement around the factory in May 2025 officially became a city. The name given to it was obvious: Starbase, Starbase. And every new rocket of this city will begin the same way, with a roll of steel at the low gates of the factory on the shore of the Gulf of Mexico. Write in the comments everything you think about this and subscribe to the channel for the richest. Here it is about luxury, wealth, and the lives of the most influential people on the planet. Thank you for watching, and right now watch our previous episodes, which have already appeared on your screen.